Something really fundamental: gravity. One of those big mysteries science keeps chipping away at.
Absolutely. And our mission today is maybe a bit unusual. We're not just recapping Gravity 101. We're looking at this, let's say, alternative idea called frictional gravity.
Yeah, this hypothesis that gravity's, well, basically friction. Sounds kind of simple, maybe intuitive even.
It does on the surface. The core claim is that gravity itself is frictional, meaning everything, planets, stars, galaxies, is constantly losing energy, spiraling inward, orbital decay, basically, as the default.
And it doesn't stop there. It suggests the universe expands just because this friction isn't strong enough between distant galaxies. So, like, no need for dark energy.
Exactly. And it even takes a shot at special relativity, claiming it's flawed because it should predict collapse, not expansion, which is quite a claim.
Okay, so it's bold. Our goal here isn't just to shoot it down, though. We want to use it as a springboard,
Yeah.
to really clarify why scientists are so confident about our current understanding of gravity, orbits, and the cosmos.
Precisely. We'll walk through Newton, Einstein, modern cosmology, the whole journey.
Hopefully giving you that aha moment about how things really work based on the evidence.
Yeah.
So let's dig in.
Oh.
So first things first, unpacking this frictional gravity. The idea is gravity acts like drag, constantly slowing things down, pulling them closer.
Right. And this is where we hit the first major hurdle. We need to be really clear about what friction is in physics.
Okay.
Friction isn't fundamental. It's what we call an emergent force. It comes from, essentially, electromagnetic interactions between atoms on surfaces that are touching. Think microscopic bumps grinding against each other.
So it needs contact, like tires on a road or rubbing your hands together.
Exactly. It opposes relative motion between surfaces in contact, and its key features are, well, it depends on how hard the surfaces are pushed together. What they're made of, rubber on tarmac is different from skates on ice.
Mm.
And crucially, it's dissipative.
Hmm.
It always removes kinetic energy from the system, turning it into heat, sound, whatever. It's a contact force, and it makes things lose energy.
Okay, that seems clear. So how does that compare to gravity? Because gravity works over, like, empty space.
Totally different category. Gravity is one of the four fundamental forces. Newton's law tells us every bit of mass attracts every other bit of mass. It's universal, works for planets, stars, apples, anything with mass.
And no contact needed.
Nope. Acts across vacuum, across immense distances. And here's the really big difference.
Yeah.
In a simple system, like just Earth and the sun, gravity is conservative.
Conservative.
Meaning the total mechanical energy that's kinetic plus potential energy stays constant. Energy just shifts between motion and position. As Earth gets closer to the sun, it speeds up, more kinetic, less potential, and as it moves farther away, it slows down, less kinetic, more potential. But the total isn't lost as heat, like with friction.
Ah, okay. So calling gravity frictional it's mixing up completely different types of forces,
Yeah.
like apples and oranges, fundamentally.
That's a great way to put it. It's a category error. You're trying to give gravity the properties of friction, dissipative, contact-dependent, material-specific, when it's actually fundamental, non-contact, universal, and conservative.
And the implication of frictional gravity would be that all orbits must decay.
All right.
Everything should be losing energy constantly.
Constantly spiraling inwards, which, spoiler alert, isn't what we generally see. Now, that doesn't mean things never spiral inwards.
Right, but maybe not, because gravity itself is friction.
So you mentioned something called dynamical friction. Is that related, or is that different again?
It's different, but it's a real astrophysical process that does create a drag-like effect. It's important to understand the distinction.
Okay, so what is it?
Dynamical friction happens when something massive moves through a medium, like a sea of smaller things. Imagine a big star moving through a dense cluster of smaller stars, or a satellite galaxy moving through the halo of a bigger galaxy.
Like moving through a crowd. Sort of, yeah. The massive object's gravity pulls the nearby smaller objects towards it. This creates a kind of dense wake behind it.
Ah, like the wake behind a boat.
Exactly. And the gravity of that dense wake pulls back on the massive object, slowing it down. It loses kinetic energy and its orbit decays. This is actually how we think galaxy mergers often happen. Smaller galaxies get dragged into larger ones by dynamical friction.
Okay, I see. But the key difference here is it needs that medium, that crowd of smaller things.
Absolutely critical difference. Dynamical friction requires a surrounding medium. It doesn't happen in a vacuum. The frictional gravity hypothesis claims friction is part of gravity itself, even in empty space.
Whereas dynamical friction is an effect of gravity interacting with stuff.
Precisely. And its strength depends on things like the density of that medium, the object's speed relative to the medium. It's complex, not the simple mass and distance relationship of fundamental gravity.
So dynamical friction is real. It causes orbital decay in specific situations, but it actually reinforces that gravity itself isn't inherently frictional. It's an interaction effect.
You nailed it. It shows gravity can be involved in drag-like phenomena, but only under certain conditions involving a medium. It completely undermines the idea that friction is a built-in property of gravity.
Okay, that distinction is clear. Let's move on to orbits themselves. The frictional gravity hypothesis predicts constant decay, right? Everything's spiraling in.
That's the core prediction for orbits. Unstable, always decaying.
But when we look up, especially at our own solar system, that's not what we see, is it? We see stability. Billions of years of it.
Exactly, and this is where Newton's framework was so revolutionary. His law of gravity provided the explanation for that stability.
How so? What's the Newtonian picture?
It's a beautiful balance. You have a planet, say Earth, trying to move in a straight line because of its inertia, its momentum.
Okay, wants to fly off in a straight line.
But the sun's gravity is constantly pulling it inward. Not slowing it down in its direction of travel like friction, but pulling it sideways, constantly bending its path.
Acting as the centripetal force, the force that keeps something moving in a circle or an ellipse.
Precisely. And it's this perfect ongoing balance between the outward inertia and the inward gravitational pull that creates a stable, closed orbit.
And this is backed up by math, by conservation laws.
Absolutely. Conservation of angular momentum is key here. It mathematically guarantees that in a simple two-body system without external forces or friction, the orbit remains stable. The planet speeds up when closer, slows down when farther away, precisely to keep that angular momentum constant and maintain the ellipse.
And the proof is in the pudding, so to speak. Our solar system, 4.5 billion years, and the planets are still happily orbiting.
It's probably the most stunning piece of evidence against inherent frictional decay. Yes, there are tiny gravitational nudges between planets' perturbations, but they cause small oscillations, predictable changes, not a systematic death spiral.
So Newton gives us stable orbits. Then Einstein comes along with general relativity and changes the picture again, but still predicts stability.
He changes the concept of gravity fundamentally, but yes, stability remains the norm. GR doesn't see gravity as a force pulling across space. Instead, mass and energy warp the fabric of space-time itself.
The rubber sheet analogy.
Huh?
Bowling ball curving the sheet, and a marble rolls along the curve.
That's the one. Objects like planets aren't being pulled by a force. They're simply following the straightest possible path, what we call a geodesic, through this curved space-time.
So it's like driving straight on a road that happens to be curved. You're not fighting friction, you're just following the road.
Exactly. The planet is essentially in free fall along its geodesic path. There's no inherent friction or drag in this picture either.
And GR made even more accurate predictions than Newton, didn't it? Like with Mercury.
Its most famous early triumph. Mercury's orbit isn't a perfect ellipse. The point of closest approach, the perihelion, slowly rotates around the sun. Newton's theory couldn't fully explain the amount of rotation.
But a GR could.
Perfectly. GR predicted exactly the observed amount of this anomalous precession. It's not decay. It's a stable, predictable rosette pattern caused by the way spacetime is curved near the sun. Another confirmation of stability, explained beautifully by GR.
So both Newton and Einstein predict stable orbits, ellipses, or precessing rosettes, directly contradicting the decaying spiral of frictional gravity.
Correct. The models that actually match observations predict stability.
Okay, but things do sometimes fall out of orbit, right? We see satellites needing boosts. We hear about planets getting consumed by their stars eventually. How does that fit in if gravity isn't frictional?
Good point. Orbital decay is real, but it happens because of specific secondary mechanisms that are perfectly understood within standard physics, and crucially, they are not gravity itself being frictional.
Okay, so what are these mechanisms? Like satellites in low orbit.
That's the classic example. Atmospheric drag. Satellites in low Earth orbit, even though space is near empty, still encounter tenuous gas particles from the upper atmosphere. These tiny collisions add up, creating drag, actual friction, which removes energy and causes the orbit to decay. That's why the ISS needs regular reboosts.
So that is friction, but it's atmospheric friction, not gravitational friction.
Yeah.
And it doesn't apply to, say, Mars orbiting the sun.
Exactly. Mars is in a much better vacuum. Another mechanism is tidal interactions.
Tides. like on Earth.
Similar principle, but more extreme. If you have a massive planet orbiting very close to its star, a hot Jupiter, the star's gravity raises huge tidal bulges on the planet, and the planet raises bulges on the star. As these bulges get dragged around, the internal flexing and friction within the planet and star dissipate energy as heat.
So like internal friction from being stretched and squeezed.
Pretty much. This steals energy from the orbit, causing it to decay. We've seen this happen with planets like WESI SP12, but again, it requires specific conditions. Close orbits, massive bodies. Not relevant for most planets in our solar system.
Okay. Any others?
One more, and this one comes directly from General Relativity, gravitational wave emission.
Ah, the ripples in space-time.
Exactly. Einstein predicted that any two orbiting masses should radiate energy away in the form of these gravitational waves. Losing energy means the orbit must decay.
So GR does predict decay. Doesn't that support the frictional idea?
It predicts decay, but the amount is critical. For something like the Earth orbiting the Sun, the energy loss is minuscule, something like 200 watts.
Like a couple of old light bulbs? That's it.
That's it. It's completely negligible over the age of the solar system. The decay is happening, theoretically, but it's incredibly, incredibly slow.
But we have detected this effect.
Oh, yes. In extreme systems like binary pulsars, pairs of super dense neutron stars orbiting each other very closely and rapidly. The Hals-Taylor pulsar was the first example. Its orbit is decaying exactly as predicted by GR due to gravitational wave emission. It won a Nobel Prize.
Wow. So it's another stunning confirmation of GR, and it shows decay happens, but through a specific GR mechanism, not because gravity is friction.
Precisely. The fact that we need these distinct, separate explanations, atmospheric drag, tidal forces, gravitational waves for the rare cases of observed decay, actually proves that decay isn't the default. It's the exception, driven by specific physics, not an inherent property of gravity.
And looking at the big picture, the solar system's future, it's stable, right, even with all the planets tugging on each other.
Well, stable is interesting. Even Newton worried if the mutual pulls between planets might eventually mess things up. Modern computer simulations, though, show remarkable stability for billions of years. No systematic frictional decay.
But the orbits aren't perfectly fixed, are they? You hear about ice ages being linked to orbital changes.
Right, those are the Milankovitch cycles. Gravitational tugs from other planets cause Earth's orbit to wobble slightly over long timescales, changes in its eccentricity, how elliptical it is, its axial tilt, and the wobble of its axis precession.
But these are cycles, back and forth.
Exactly. Predictable, cyclical variations. They drive climate change like ice ages, but they are stable oscillations, not a one-way trip towards the sun.
Okay. And what about this idea of chaos in the solar system? Does that mean it is unstable?
Chaos in the mathematical sense. It means the system is extremely sensitive to initial conditions. Tiny uncertainties now make precise predictions billions of years ahead impossible. It does not mean the system is about to fly apart.
So it's like, we know the planets will stay in roughly their current lanes, but predicting exactly where Mercury will be in 5 billion years is basically impossible.
That's a good way to think of it. It's bounded chaos. The orbits remain broadly similar, stable within limits, even if their exact long-term future is fuzzy. It's a feature of complex gravitational interactions, absolutely not evidence for frictional decay.
Okay, so on the scale of planets and orbits, the frictional gravity idea really doesn't hold up against observation or theory. Let's zoom out now. The hypothesis also made claims about the whole universe, right?
It did. Two main claims. That the universe expands simply because there isn't enough frictional gravity between distant galaxies, and that special relativity is somehow flawed because it doesn't predict cosmic collapse.
Let's tackle the relativity point first. That sounds like a misunderstanding of what special relativity even does.
It is, fundamentally. Special relativity, Einstein's 1905 theory, deals with physics in the absence of gravity. It describes how space and time are related for observers moving relative to each other, leading to things like time dilation and length contraction, EMCAOI. But it specifically works in flat space-time.
Meaning no gravity.
Right. So it simply makes no predictions about whether the universe as a whole should expand or contract, because that's fundamentally a question about gravity's large-scale effect. Applying SR to cosmology is the wrong tool for the job.
So which tool is the right one?
General Relativity, Einstein's 1915 theory. That's our theory of gravity, describing it as space-time curvature. And when physicists like Einstein himself, Lemaitre, Friedman, applied the Einstein field equations to the universe on the largest scales,
What did they find?
they found the equations naturally described a dynamic universe, a universe that had to be either expanding or contracting. A static universe was unstable in GR. So far from being a flaw that GR didn't predict collapse, it actually provided the mathematical framework that predicted cosmic dynamics, expansion or contraction.
And observations then showed it was expanding, Hubble's law in the 1920s.
That was the first major piece of evidence. Hubble observed that distant galaxies are redshifted, meaning they're moving away from us, and the farther away they are, the faster they recede. V equals h times d, classic Hubble's law.
But the frictional gravity idea could maybe try to explain simple expansion as just coasting apart due to lack of friction. How do we know it's more than that?
Because in 1998 came the bombshell discovery. The expansion isn't just happening, it's accelerating.
Right, the supernova results. How do they figure that out?
Using type Ia supernovae. These are exploding white dwarf stars that reach a very consistent peak brightness, making them excellent standard candles. We know how bright they should be, so by measuring how bright they appear, we can calculate their distance very accurately.
Like knowing the wattage of a distant light bulb to tell how far away it is.
Exactly. And two independent teams looked at very distant supernovae. They found these supernovae were consistently fainter than expected, even for a universe coasting or slowing down.
Fainter means farther away.
Farther away than predicted. For the light to have traveled that extra distance, it must have taken longer, which means the universe must have expanded less quickly in the past than it is expanding now. The expansion has sped up.
It's accelerating. And that completely rules out the idea of just coasting apart due to lack of friction, doesn't it? You need something actively pushing.
Precisely. Simple coasting wouldn't accelerate. Deceleration due to gravity was actually expected. Acceleration requires some kind of repulsive energy driving things apart faster and faster.
Enter the standard model of cosmology. Lambda CDM. CDMPO. What does that stand for, and what's in it?
Lambda represents dark energy, the component causing acceleration. CDM stands for cold, dark matter. It's the framework built on general relativity that best explains our observations of the universe.
Okay, so break down the cosmic recipe according to CDM. What's the universe made of?
It's quite humbling, actually. Ordinary matter, the stuff atoms are made of, stars, planets, us, everything we see that's only about 5% of the total energy density of the universe.
Just 5%. Wow. What's the rest?
About 27% is cold dark matter. Dark because it doesn't emit, absorb, or reflect light, so we can't see it directly. Cold means it moves relatively slowly. And matter because it has mass and interacts via gravity.
But how do we know it's there if we can't see it?
Through its gravitational effects. The way galaxies rotate, stars on the outskirts move way too fast if only visible matter was providing the gravity. Gravitational lensing light from distant objects bends as it passes massive structures, revealing far more mass than we see. Dark matter provides the extra gravitational pull needed to explain these observations. It basically formed the invisible scaffolding upon which galaxies and clusters formed.
Okay, so 5% ordinary matter, 27% dark matter. That leaves 68%.
Yep, the biggest chunk, dark energy, represented by lambda. This is the mysterious component driving the accelerated expansion.
So dark energy is the opposite of the frictional gravity idea. It's not a lack of pull, it's an active push.
Exactly. It's an active agent of repulsion. In GR terms, it has a large negative pressure, which, perhaps counterintuitively, creates repulsive gravity. The simplest model is the cosmological constant, an intrinsic energy density of empty space itself.
So as space expands, you get more space, and thus more of this repulsive energy.
That's the idea behind the cosmological constant. As the universe expands, the density of matter and radiation drops, but the density of dark energy remains constant. Eventually, it starts to dominate, overwhelming gravity's pull and causing the expansion to accelerate.
And the existence of dark matter flatly contradicts the frictional gravity claim that gravity is too weak between galaxies, right? Dark matter means there's more gravity than we thought.
Absolutely. It goes back to Fritz Zwicky in the 1930s looking at galaxy clusters. The galaxies were moving too fast to be gravitationally bound by the visible matter alone. He called it the missing mass problem.
And Vera Rubin's work on galaxy rotation curves really cemented it.
Definitely. Her observations in the 70s showed stars in the outer parts of spiral galaxies orbiting just as fast or even faster than stars closer in. Newtonian gravity with just visible matter predicts speeds should drop off. The only way to explain the flat rotation curves was a huge halo of invisible dark matter surrounding the galaxy, providing extra gravity.
So we have overwhelming evidence for extra gravity on large scales, dark matter, and for an active push causing accelerated expansion, dark energy. The frictional gravity idea seems completely at odds with cosmological observations.
It really is. The universe's history seems to be a tug of war. For the first 9 billion years or so, gravity from both ordinary and dark matter was winning, slowing down the initial expansion and allowing structures like galaxies to form. But around 5 billion years ago, as matter spread out and its density decreased, the constant repulsive effect of dark energy started to dominate, and the universe transitioned into the accelerating phase we see today.
So wrapping this all up, going through this frictional gravity idea, even though it doesn't hold water, has actually been really useful for highlighting why the standard models work so well.
It's a perfect example of the scientific method. You take a hypothesis, even an intuitive one, and you test it rigorously against observation, experiment, and mathematical consistency. If it fails those tests, like frictional gravity does, it has to be discarded or modified.
Let's recap the key failures. First, the fundamental mismatch. Friction is dissipative, contact-based, emergent. Gravity is conservative, non-contact, fundamental.
Right. Second, orbital mechanics. The observed long-term stability of the solar system, Mercury's precession explained by GR, and the fact that real orbital decay needs specific secondary causes like drag, tides, or gravitational waves, none of which mean gravity itself is frictional.
And third, cosmology. Misapplying special relativity, ignoring the overwhelming evidence for accelerated expansion driven by dark energy, and missing the crucial role of dark matter, which shows gravity is actually stronger than expected on large scales, not weaker.
Exactly. It fails on pretty much every front when confronted with evidence.
It really underscores the power of our current frameworks, like general relativity and the lambda CDM model.
Yeah.
They might not be we still don't know what dark matter or dark energy are, fundamentally.
But their ability to explain such a vast range of phenomena from tiny orbital shifts to the universe's expansion is just incredible. Their predictive power and consistency with observation are unmatched by any alternative so far. They represent our best understanding, built on centuries of scientific inquiry.
It really is an amazing picture. Which leaves us maybe with a final thought for you, the listener.
Yeah.
Given the successes, what are the real frontiers now? What are the deepest puzzles remaining within GR and lambda CDM, like the true nature of dark matter and dark energy? And what might the next generation of telescopes and experiments reveal that could perhaps lead to the next revolution in our understanding of the cosmos? Something to ponder.